Thank you very much. So indeed, this is the last of my three mini-course lectures. So I'll try to wrap up a little bit. So yesterday we stopped here about network modeling and about small world properties. And I didn't quite deliver on this statement that distances are remarkably similar across models because I had only discussed distances in one model. So I'll continue with that. And this is a result that is very similar to the result we've already seen for the configuration model. Now it's applied to the generalized random graph. I've been trying to convince you of the fact that these models are actually highly related. So the statement that distances are very similar in these two models should also not really come as a surprise. The only thing that you see is that there is a different form for the precise parameter nu that describes when the branching process approximation becomes supercritical. And in fact, there is a little bit of an explanation there because I've been explaining that the configuration model and the generalized random graph are very closely related. And for the configuration model, we have a very similar result as here, namely saying that if a certain parameter nu is larger than 1, then the graph distances behave like log n over log nu. Okay? But for the configuration model, this nu parameter was the expected value of the degree times the degree minus 1 divided by the expected value of the degree, which looks a bit different from what we see over here. But you should bear in mind that for the generalized random graph, we've already seen that the degree distribution in the graph actually is Poisson with random weight distribution W, which is the limit of the weight sequence. And we know that...
Can you just define Hn again?
Oh yes, very good. So Hn, and it will come up a lot, is the graph distance between two uniformly chosen vertices. In my vertex space, 1 up to n. Now, in this case, the giant component is not everything, and therefore we do have to condition this graph distance to be finite. That actually means that the two vertices are going to be in the same connected component, and because there is a unique giant component in these settings, this actually means that they're, with very high probability, actually both going to be in the giant component. So what this object measures is distances within the giant component. And this actually ensures exactly that there is a giant component. Thank you for the question. Okay, so I was trying to explain that this nu parameter actually is the same as that nu parameter. And that is because the degree distribution in the generalized random graph is Poisson with this random parameter. And we also know that the expectation of a Poisson random variable with the parameter lambda times the Poisson variable with the parameter lambda minus 1, so counting down the factorials, this actually is the square of the parameter. So applying that here, we're actually going to be seeing that the top is the expectation of W squared and the bottom is the expectation of W. So we see that the nu parameters are actually the same thing, it's just that they're written in a slightly different form. Okay? And you should bear in mind that nu larger than 1 is exactly the same thing as saying that there is a giant component. Now, if we're in a graph where there's no giant component, it doesn't make much sense to talk about distances, because you have these all very small components, and okay, what does the distance mean? All right, so this is the kind of result that we've seen for the configuration model, in fact, identically the same with a value of nu that is actually closely related. And then the second theorem says that when we're in a situation where the second moment is infinite, so that means that tau is in between 2 and 3, you need some extra conditions on the weight distribution, the empirical distribution of the weights. And then the graph distances between two uniformly chosen vertices again grows like a constant times log n. And in fact, the constant is the same as the constant for the configuration model. So these results are really identical. And there's also extensions for the diameter. We've seen results about the diameter in the configuration model yesterday, but you should bear in mind that in the generalized random graph, diameters are always logarithmic, because there's lots of vertices with degree 2. Okay? And I was referring to this very general paper by Bolobach, Janssen, and Reardon about inhomogeneous random graphs. So this is much more general than the setting of generalized random graphs that we've been looking at here. But they prove a result such as this, and then also asymptotics for the diameter in this level of generality. So this is really a very, very profound paper. All right. So these were distances in 2 of the models, and we see that they are almost identical. Now the third model that we've been spending some attention to is the preferential attachment model. And I've already been telling you that these preferential attachment models tend to be much harder than configuration models and generalized random graphs. And that's because of their dynamic nature. So if we look at a graph that is very big and now we pick 2 vertices uniformly at random, then, well, when have these vertices arisen? And this really creates difficulties in trying to understand, for example, graph distances between vertices. So our control in this setting is much less. Nevertheless, sort of the whole phenomenon of universality, physicists have been predicting that graph distances and many other properties in preferential attachment models should behave very similarly to those in the configuration model when you would give the configuration model the same type of degree distributions as the preferential attachment model has. So in particular, looking at theorems such as this, but then for the configuration model, you would be led to believe that in preferential attachment models, if they have a finite second moment of the degrees, distances should be logarithmic, and if they have an infinite second moment of the degrees with a power law tau in between 2 and 3, then actually distances should be log-log. Okay? So that's what the physics predictions tell you. And this is sometimes called universality again. So in general, this is a much harder problem because we have far less control over distances in preferential attachment models, but there are some results in this direction. So the first result is in a paper from Bolobach and Reardon, already very early on. They show that the diameter of the preferential attachment model, when delta is equal to 0, so this is the Albert-Barabasi model, actually has this funny behavior, log n over log n. Now what you should bear in mind is that for preferential attachment models, I'll write this down. So what we're trying to say is that preferential attachment models and configuration models with the same power law exponent should behave similarly. So it's actually useful to recall what the power law exponent was for preferential attachment models. And you should bear in mind that this delta here was the sort of the constant that we add to the degrees. And we're attaching proportional to the degrees plus a constant, and this constant is delta. And the m variable was the number of edges that come with every vertex. So a vertex comes in with m edges and attaches those in one way or another in a preferential attachment form. So if delta is equal to 0, that means that tau is equal to 3, and this is precisely the boundary case here. So this you should really think of as being tau greater than 3, and this is tau strictly in between 2 and 3, so tau is 3 is on the boundary. Okay? So we've long been in a situation where we had pretty precise results for the configuration model. We had one very precise result about the preferential attachment model, but the range at which these results were applying was completely disjoint. So it was very difficult to check the universality result. In fact, it turns out that you can show that also in the configuration model, if you have a power law exponent that is precisely equal to 3, you also see these log n over log n distances. Okay? So that was the very first result. I'm naming it here because it's an important result. It was one of the first results about distances in preferential attachment models. Now in the general case, when tau is strictly in between 3 and infinity, the second moment is bounded, we have fairly poor control over the structure of the graph. So it's difficult to prove precise results. What we can show is that with high probability, the diameter is of order log, and also the typical distances are also of order log. That actually means that with high probability, this hn, the graph distance between 2 uniformly chosen vertices between 1 and n, is in between 1 over epsilon times log n and epsilon times log n, where epsilon is some finite constant, some strictly positive constant.
So the proof techniques in the first Piyush's paper, Probabilistic paper, they're very specific to tau equal to 3. They don't
Yes.
generalize in it?
Yes. They have a very specific rewrite of the model, a different interpretation of the model that is only valid for delta is equal to 0. Yeah. It's called the LCD description. There's a lot to be said about this because there's later papers by Berger, Borks, Chase, and Saberi that give a very clever description of the preferential attachment model based on Earn schemes. So they have some independent random variables associated to the nodes, and conditionally on these independent random variables, what you get is sort of independent edges. That's a beautiful description. It's very closely related to Earn schemes as in, let's say, Polya Earn schemes, where also you see that by the Finetti theorem, the different sort of the choices of the balls are conditionally on some limiting random variable, IID. But that description is still quite complicated, and it has not been sort of pushed further in order to get very precise asymptotics for diameter and graph distances. I'm expecting that this will be done at some point. I know that there are some people thinking about this. So, funnily enough, there is a result in this regime where tau is in between 2 and 3, and there the result is sharp. So the result says that again, if you look at the graph distance between two uniformly chosen vertices in the graph of size n, if you divide through by log n, you get a constant again. And the constant is very similar to the constant we've seen before, except that here it's 2, and here it's 4. So distances are twice as big. Okay? Same order asymptotics, it's just that the constant is quite a bit bigger. And I would like to spend a little bit of time trying to explain how you can understand how this arises, this factor 2. Where did I put the chalk? So, as a first warm-up question, why are distances so small? Why are distances so small in real-world networks, in general? Well, the way how I've come to think about this is that any individual knows a person who's much more influential than the person, him or herself. So I always compare myself to the rector of the university, and the rector of the university moves in quite different circles than I do. So that person is actually much more powerful than I am, and therefore actually this person also knows many more, even more powerful people. Okay? So suppose I would like to argue that everybody within the Netherlands is actually a distance 4, 5, or 6 from one another. How could one argue that? Well, you could say that everybody knows somebody who is much more influential. That person again knows somebody who's much more influential. If you don't have to go pretty high up in order to get to the king of the Netherlands or the former queen of the Netherlands. And if everybody can do that in 2 or 3 hops, then actually everybody's at 4, 5, or 6 hops away from each other. Okay? That's actually a very compelling picture. So the previous rector of the University of Eindhoven shook hands with our previous queen when the university existed for 50 years. Now I've shaken hands with the previous rector, so therefore I'm a distance 2 from the queen. Okay? If you can do this for everybody, you're there very quickly. Now this of course is a bit of a metaphor, but actually there's a lot of truth in it. So the truth that you see in it is that somehow individuals who are quite powerful tend to be connected to some rare individuals that are even more powerful than they. Much more powerful. So what is the translation of this in the random graph setting? So in the configuration model, what you see, suppose I'm an individual and I'm powerful. That actually means that I have a degree, and I'll denote this by little d, that is quite large. I will not specify this. Now, the most powerful person to which this individual is connected is the person of highest degree. So let's suppose that tau is in between 2 and 3. So this is the setting that we're led to believe should be true in many applied settings. Then it turns out that for the configuration model, the highest degree vertex to which this vertex V is connected is of order d to the power 1 over tau minus 2. So it's a power of the original degree, dv, raised to a power that is strictly larger than 1. Tau is in between 2 and 3, and therefore 1 over tau minus 1 is strictly larger than 1. So that actually means that if I start with an individual of fairly high degree, in one step, I'm a power larger than 1 larger. In 2 steps, it's that power squared. In 3 steps, it's that power raised to the power 3. So how often do I need to do this before I start seeing vertices of degree of maximum degree? Maximum degree being some power of n. Well, that's exactly, so the number of iterations needed to reach a degree n to some power alpha is roughly log n divided by log tau minus 2. Because you basically, what you need to do is you need to iterate as long as this to the power k becomes of the order log n. And solving that equation will give you log n over log tau minus 2. And in fact, if this is a tenth, then in one go it will be, well, 1/10 divided by tau minus 2. And in 3 goes it will be this divided by tau minus 2 to the power 3. So in a few hops you can go from 1 over 100 to 1 basically, or a half. Okay? So this is almost exactly the distance that we see, apart from a factor 2. And the way how you should think about this is that I pick 2 vertices uniformly at random. It's very likely that a shortest path will actually go through one of the hubs, a vertex with very high degree. So actually they both need to reach the hub. Okay? So the hub, reaching a hub takes about this long, so graph distances are twice this big. Okay? Very simple explanation. Now for the preferential attachment model, this is not true. Because you should bear in mind that in the preferential attachment model, the hubs are the old vertices. So if I'm some sort of a vertex with pretty high degree, I'm somewhat Earlish, but not extremely Earlish. So I will be connected to a vertex that is roughly equally early as B. Whereas if I want to get my degree to be much larger, the vertex should really become a lot earlier. That's not going to happen. Okay? So that seems to be indicating the distances should be much larger. But there's another effect that comes into the preferential attachment model, and that is the idea of interconnectors. So suppose I have a vertex J that has pretty large degree, or let's call it V again to be consistent. So the degree of V is quite large at a given time. And now suppose I want to connect it to a vertex that has a much higher degree, roughly of this order of magnitude. And I'm not going to do that in one go, but as it turns out, there will be another vertex, J, which will be connected to both. So here, the degree of V, let's say at time t, is quite large. Then it will be connected to a vertex that has roughly degree of V raised to the power 1 over tau minus 2. But in 2 steps, not in 1 step. But that actually implies that distances are twice as large. Now this, of course, is a very sort of caricature picture, but it turns out that this picture is actually correct. And you see that coming back in the fact that the 2 really is replaced by a 4 here. So this is an intuitive explanation, first of all, where these distances and the logarithmic nature, the doubly logarithmic nature comes from, but also why these distances are twice as large in the preferential attachment model compared to the configuration model. And it also highlights a huge difference in these models. So in the configuration model, vertices of very high degree tend to be directly connected to other vertices of even higher degree. Whereas in the preferential attachment model, that is not true. So this is really a topological difference between the 2 models. So this is sort of also partially an answer to the question whether these models are going to be alike. Yes, they're going to be alike, they behave very similarly, but if you look very quantitatively, they really do behave differently. Okay? And it turns out that in this regime, we can also compute the exact form of the diameter, and in fact this has also been done for the configuration model, and that in this regime it turns out that this diameter is log n again. And you see here the constant for the typical distances, and then there is an additional extra term which you can compute explicitly. And the way how you should think about this extra constant is that, for the diameter you have to look at very rare individuals, for which somehow their local expansion is very slow. Well, the slowest you can expand for a preferential attachment model is when somehow locally you're a tree that has minimal expansion. But every vertex that appears in a tree has degree at least m plus 1, because there's one edge coming into it, and then there's m edges going out. And you can compute that the probability of having one of these traps of depth log n times a certain constant, that becomes of the order 1 over n when you take the constant exactly this. So that's how this comes about. You somehow need to connect two vertices that are most locally trapped. And once you get out of the trap, the distances are very much alike the typical distances. So that's how this is built up. Okay? So distances are remarkably similar across models with detailed differences due to the structure of the precise models. Okay, so here I've repeated the result for the configuration model because I would like to say something about how this is being proved. I've done it there sort of at a very a loose level, very intuitive, but how is this done in more detail?
You said
Yeah.
in the preferential attachment model, the older nodes tend to be more popular than the newer ones.
Yes, the old get richer.
Is there a precise way of saying this?
Yes, there's absolutely a precise result about this. And the precise result says something about the degree structure of the first few vertices. So look at di of t, where I now think of I as being fixed, let's say 1, the very first vertex, and I let t tend to infinity. It turns out that if you divide this through by t to the power 1 over tau minus 1, which would be precisely the maximum value of a sequence of t IID random variables with power law exponent tau, then this converges almost surely to some limiting variable, xi, and this one is strictly positive almost surely. Okay? So the degrees grow like t to the power 1 over tau minus 1. And it turns out that also the maximum degree behaves like this, and that the index which reaches the maximum degree actually is some finite index. Okay? So this is for I being fixed. But if you somehow scale I and t simultaneously in such a way that I is still smaller than t but can grow, then it is the case that di of t is very closely related to t over I raised to the power 1 over tau minus 1. And this was exactly how I was choosing my degrees in the configuration model when I was assuming that there was a power law tau. So all of these sort of characteristics of the degree structure are very well known and are very similar to what you would expect for IID degrees. But they're not IID degrees. So the maximum degree scales in the right form, but the limiting random variable is really different.
Zeta is a random variable.
Yeah.
And what does it have?
So, I mean, the way how to prove this is using a martingale. So you can write this, if you add delta, that's actually a nice martingale. And then this is the martingale limit. And we generally don't know very much about martingale limits. In the case where delta is equal to 0, this is square root of t, and then much more is known about the limit. But in general, we know very little about it. I mean, the beautiful thing about martingale convergence theorem is that it will give you almost sure convergence. In general, that's very difficult to prove. The downside of it is it gives you very little control over the limit. So for example, for branching processes, if you look at the generation size, finite mean, you divide through by the mean of mean offspring to the power n, and you take the limit, you get a nice limit. But actually there's not a lot is known about the precise structure of the limiting random variable. And it's very similar here. All right. Okay. So how can we understand these results sort of on a slightly more formal level? Well, what you could do, and this was sort of the picture that I was drawing, is you can take your two vertices and you can locally start growing the neighborhoods from them. And of course, at the first moment when these neighborhoods start overlapping, that will be the shortest path. That will be the shortest distance as well. So what does actually a neighborhood look like? Well, I start from one vertex, and I know exactly what the limiting distribution at that vertex is, because I'm assuming that my degree distribution converges in distribution. So if I take a uniform vertex, then the law of this will be this dn. That's the same thing as the degree of a uniformly chosen vertex. And that will actually converge in distribution to some limiting random variable. Okay, so I know how many, well, edges or half edges for the configuration model in distribution are going to come out. If I want to then iterate, what I need to do is start pairing these half edges, and I need to pair them appropriately, uniformly at random amongst the half edges. And then actually what will happen is I'll actually take one of these half edges, and then there's a few more half edges coming out of this. In this case, the degree of the vertex is 6, and that means that there's 5 more half edges coming out. So what is the probability of pairing one of these half edges to a vertex that has degree 6, for example? That's then the question. Well, you can do the arithmetic. Here I'm writing sort of A is one of these neighbors, that's this vertex. And I'm looking here at this B of A variable, that's the number of half edges that are incident to the vertex, not counting this one. That's of course the same thing as the degree of that vertex, minus 1. Okay? And then I can compute what the probability is that this BA is exactly K. Well, that actually means that I'm attaching to a vertex of degree K plus 1. And if the probability of attaching to a vertex of any vertex of degree K plus 1 is K plus 1 divided by the total number of half edges. So that's K plus 1 divided by the sum of the degrees, and that's what I've been denoting by ln all the time. Okay, so this is the probability of attaching to any vertex of degree K plus 1, but I may have many more. Generally, for a fixed K, I have n of them. So that actually means that I need to post-multiply by the total number of vertices that have exactly the degree K plus 1. And now what I can do, this is K plus 1 is going to remain fixed, but I can divide this through by n, and then also divide this through by n. Then what I'm going to get here is exactly the expectation of dn, which actually converges to the expectation of d. That's what we get over here. And if I divide this through by n, I get exactly the probability that dn is equal to k. Okay? So both of these converge, and they converge in probability when they're IID, for example, to this limit, k plus 1 divided by the expectation of d times the probability that the degree is k plus 1. Okay? So this has some size biasing to it, because we multiply the value, we multiply the probability of taking a certain value by that value and then divide through by the expectation. So that's a size bias distribution, but in general we don't have the plus 1, and the plus 1 actually makes sure that the distribution is shifted by 1. So we don't get the size bias distribution by itself, but we get the size bias distribution of d minus 1. So we generally denote the size bias distribution by d star, and then this random variable will converge in distribution to this d star minus 1. Now in general, this actually is a finite random variable, even when tau is in between 2 and 3. And that actually means that if I pair one half edge, I'm actually only going to see a tight number of other half edges that is connected to it. So after one pairing, the total number of half edges that is involved in this graph is going to still be a tight random variable. Now in total I have ln half edges, so if I start pairing this one, actually the distribution of what it will be paired to is going to be very insensitive to what has happened here. That means that it's almost an independent version of whatever happened here. And the same is going to be true here and there, etc. Right? So if I want to draw it like this, then asymptotically, this number of half edges is going to be independent of that number of half edges, and these are going to be independent of the number of half edges chosen here. And then you can iterate. But if all of these are independent from one another, then what I get is a branching process. It's a bit of a peculiar branching process because the root offspring distribution is different from the offspring distribution from everything else. The reason for that is that this vertex has been chosen uniformly at random, whereas this half-edge has been chosen uniformly at random. And that makes a hell of a difference. Okay? So what we see is that in the end, we see that all of these random variables, at least when we do this a finite number of times, will converge jointly, and therefore this neighborhood up to any finite distance will converge to a branching process. This is what I've been calling branching processes approximations in random graphs. Okay? So the neighborhood looks like a branching process with offspring distribution d star minus 1, well, except for the root has offspring distribution d. Now we know very well that sort of these branching processes have a positive probability of surviving forever when the expected value of this random variable is strictly larger than 1. Okay? So let's do this arithmetic. What is the expected value? Let's call this nu. Expected value of d star minus 1. Well, it's the sum over k times the probability that d star minus 1 takes the value k. And we've done the arithmetic. That is actually going to be the sum over k times k plus 1 times the probability that d is k plus 1 divided by the expected value of d. Well, that's nothing but the expected value of d times d minus 1 divided by the expected value of d. And this was exactly this new variable that I was claiming should be relevant. Okay? So this new parameter that has come up all sorts of times is just the expected number of, let's say, sibling half-edges incident to a half-edge that is chosen uniformly at random, not counting that half-edge by itself. And it's also, in expectation, the number of, let's say, further children you're going to have, discounting for the one that has been eaten up by the pairing. So it's natural to say that, you know, when this is larger than 1, then the branching process has a positive probability of surviving. Okay? Now, of course, this is a very sort of hand-waving computation. If you want to make this precise, you have to go into the area of local weak convergence. I'm not going to be doing that here. That would require a lot more time. The theory of local weak convergence is very well developed, but it's a bit tricky. But this is a way to make this a statement like this precise. Let me now try to make the link to graph distances. So when the second moment is finite, that actually means that the expectation of my branching process is finite. Okay? And we know then that these branching processes tend to grow exponentially. In fact, at rate, the mean offspring raised to the power k for the kth generation. So if I define zk to be the number of individuals in the kth generation, and I divide it through by nu to the power k, I have a martingale, non-negative, therefore it converges almost surely to a limit, and this limit will actually be strictly positive on the event of survival. Well, we need a little bit more for that. That's called Kesten's-Stigham's theorem. We actually need a logarithmic moment more, but I'm going to be ignoring this. So let's just assume that this is strictly positive. Then actually it means that in a logarithmic number of steps, we're going to see a polynomial number of vertices. That's basically what it says. And that allows you to deduce, at least informally, that graph distances in this setting should be log n divided by log nu. Because at time log n divided by log nu, this nu to the power k, if I pick k to be log n divided by log nu, this nu to the power k will be exactly n. Okay? Right. So what happens instead when tau is in between 2 and 3? Well, then we're dealing with an infinite mean branching process, and it's even a bit worse, because it's not just the mean that is infinite, but even the expectation of the offspring raised to a power 1 minus epsilon for some epsilon will also be infinity. So it's highly infinite mean. In that case, it is known, under some further regularity conditions on the distribution function, that actually the number of individuals in the kth generation will grow doubly exponentially. So you first take a log to knock out one exponential, and then you multiply by an exponentially decaying number, And that limit will then converge to some limiting random variable, y, that is strictly positive on the event of survival. So it looks a lot like here, except that zk has been replaced by the log of zk. And actually, the value nu has been replaced by 1 over tau minus 2. That's exactly this kind of thinking. So this would predict that z of k would behave like e to the power tau minus 2 to the power minus k times some random variable. And this random variable is basically characterized by what happens very early on in the game. That's exactly what this y characterizes. Okay? So if we do this, and then somehow interchange limits, and think about how long it will take, let's say, the exploration from the two independently chosen uniform vertices to reach a vertex of degree some power of n, this will take log n over absolute value of log tau minus 2 steps. And therefore the distance between them will be twice this. And that's how you can understand, from a branching process perspective, how these distances behave. Okay? Now, of course, here I'm talking about local weak convergence, and that says that the local neighborhood around the point converges in distribution to a branching process. That basically says that, whatever distance k I take, as long as k is finite, if I look at the distribution of my local neighborhood, this will converge in distribution to the local neighborhood of a branching process at the same distance. But bear in mind, here I'm actually looking at distances that grow, either like log n or like log n. So there needs to be some more fiddling around in order to make this proof stick. But the whole point is that in a branching process, after a finite number of generations, you've already basically reached this limit. And afterwards, it's just the law of large numbers that basically kicks in. It turns out that this law of large numbers, in this case, can be extended to the configuration model, and therefore the same result still applies. Here, on the other hand, the dynamics is quite different. Here what you see is that, after a couple of generations, if I look at zk plus 1, it will be zk raised to the power 1 over tau minus 2. And that's also an almost deterministic sort of recursion that takes place. And it turns out that this recursion, again, can be extended to the configuration model as well. And that's how you can somehow go from local weak convergence, the local understanding of neighborhoods, to, in fact, global properties such as graph distances. All right. So, small worlds. These results that we see, logarithmic distances and log-log distances, they allow us to quantify small world behavior, at least in random graphs. And they give us some idea, some inkling as to why we see these really small distances also in real world networks. And the thought is that 6 degrees of separation should be related to the fact that distances grow like log n, and log of 10 to the power 10 is actually not that large. So these were the results for 3 very specific models: the configuration model, rank 1 inhomogeneous random graphs, generalized random graphs, and preferential attachment models. In the meantime, there have been lots of results also extending this kind of thinking to other settings. And in general, the fact that distances grow doubly logarithmically in the setting where you have infinite variance degrees, that is true much more generally. So there are spatial versions of this, there are many other versions of this. In the random intersection graph, this is known, etc. So this is a high amount of universality that is present in these kind of random graph models. But you should bear in mind that the results that I've been talking about today are really in the setting where these graphs are locally tree-like. So they can be well approximated by branching processes. That, in fact, turns out to be true for the preferential attachment model as well. Also there, Berger, Borks, Chase, and Saberi proved that the model is converging in the local weak convergence sense. And there, the neighborhood structure is a multi-type branching process, where somehow the types indicate, let's say, the birth time of the individuals involved. Okay, so also there, in particular, you have a locally tree-like setting. So the number of triangles, for example, is much smaller than the number of vertices. So all of these results are in this setting, and it will be much more difficult to move away from such a local tree-like setting. All right. So I would like to switch gears for the last quarter of an hour. So far I've been talking about graphs and their local and global topologies, giant components, graph distances, local neighborhoods, and so on. Now, in many cases, you're not just interested in what happens locally in your graph and what the topology of your graph looks like. You're often also very much interested in what happens on such a network. And I will present one example of such a problem. This is smallest weight routing. You could think of it as a rumor spread or something like that. So we've already heard Ganesh talk about similar problems, but then Ganesh was talking about them generally on complete graphs. So here we'll be talking about them on random graphs. Okay? So let me give a small introduction to why such problems may be interesting. So yeah, in many applications, there are edge weights associated to the edges. You could think about sort of the cost of using the edge or the amount of time that it takes to use that edge. And if you think about applications, often the time delays that are encountered by communication within a network, they're generally accumulated along the vertices of the shortest path. Because at the vertex, you may have some router, the router needs to process a packet, and the packet will then be sent on, and sometimes there's time delays occurring there. Okay? So then the question becomes, I started with my graph, now I'm going to be associating a weight structure to the edges of the graph. How does that change the topology of the network? Okay? And we'll do that in the simplest of all possible settings, namely, I will just associate a weight structure that is completely IID across the edges. So every edge will receive a weight, and all of these weights are assumed to be IID. That's the simplest possible setting that you could come up with. And in fact, I've been talking a lot about graph distances and small world properties. That actually falls into this category when you take all the weights to be equal to 1. So this should really be an extension of that work. But in general, we will be assuming that these edge weights are IID continuous random variables. Okay. So what is a little bit of background as to why we could do something like that? Well, I've really been inspired in my random graphs work by trying to understand what happens on the internet. So Piet van Michem, a close colleague in Delft, when I was working in Delft, he came up to another colleague of mine, Gerard Hooghiemstra, and he was saying, okay, we have lots of measurements for, let's say, shortest paths or email, trace route data. We actually would like to understand whether we could say something about the topology of the network from this data set. What does the internet look like? Okay? And then, of course, you need to understand something of the physical background of such a model. So we started investigating, and around 2000, Cisco is the main producer of routers in the internet. It is true that in the internet, edges typically receive weights, but it's not clear what these weights are. We don't have any data about that, because that's secret information. But we do know that Cisco recommended to use link weights that are proportional to the inverse link capacity, inverse bandwidth. And that will actually guarantee that cables that are very thick, have a high bandwidth, are going to receive more traffic as you would like it. But that it's precisely the inverse of the bandwidth that's not so clear that that is the best possible way. So that basically means that if you have a proportion of link weights with value at most b, then this proportion should be equal to the proportion of edges or links with a capacity at least 1 over b. Okay? But of course, just like we don't know anything about the weight structure that is being used by the operators in the internet, we also don't know much about the empirical properties of bandwidths of cables in internet. So we're just going to be assuming that these are IID random variables. And then this returns to the problem of smallest weight routing on such a network. Okay? Now this is the kind of data that I was talking about. So this is a huge data set of end-to-end email messages where you have lots of source nodes and lots of destination nodes, and you count how many hops are needed to go between all the sources and all the destinations. And then you get a histogram that looks like this. It looks remarkably like a Poisson distribution. or maybe even a Gaussian. And actually the mean is somewhat highish, it's of the order 15. And actually the tail distribution is very, very thin here towards the end. And it better be, because at that time, an email message was killed after it was going through more than 32 hops. So if in your graph you would have a diameter larger than 32, you would be in trouble, because then you would actually not be able to communicate between the two nodes that are at either end of this long path. Okay? So the question was, does this look like a Poisson distribution? Well, yes, it does. You can actually do some statistical analysis, and it actually looks a lot like it. But then the question is, what sort of model is there that would be able to predict a result such as this? Okay? So I've been talking about smallest weight problems now in the context of internet, but of course you can also think of it in terms of rumor spread, and then the amount of time that it will take you to tell the rumor to any one of your friends would be the random variable that the link weight would characterize. But it's also important in epidemic models and in various other problems such as competition processes and so on. It's one of the most basic models of information diffusion processes on graphs. And therefore, it's interesting to investigate. And we've already heard Ganesh talk about this problem and similar problems. So what is the setting? Let's be very precise. We have some sort of a graph. And in this talk, I will mainly take G to be the configuration model. But also the complete graph has been investigated quite substantially. And then there's two objects of interest. The first is the minimal edge weight to go between one vertex and another vertex. And I will generally be assuming that these two vertices are chosen uniformly at random, just like in the graph distances, from the collection of vertices. And then what we compute is, for any path that goes from V1 to V2, we take the total cost of that path, the sum of the edge weights, and then we minimize that over the possible paths. So if all the YEs would be equal to 1, then indeed this would give us the graph distance back. I'm assuming here that the YEs are an IID collection of weights with a continuous distribution, and the reason for that is that then this minimum will be almost surely attained by a unique value. And then we can also talk about the shortest path. And that's nice, because then we can also investigate how many edges there are in this shortest path. And there would be 27 shortest paths, and it would be more difficult to talk about this object. So this is sometimes called the hop count, due to the connection to the internet problem, and this is the smallest weight. All right, so what is the main behavior for such a system? Well, here is a very general theorem that appeared 2 years ago in the Annals of Probability. So I'm again going to be assuming that I'm in the setting of the configuration model, and I'm going to be assuming that we have the weak convergence of the distribution, of the degree distribution, the mean converges, and in this case we in fact assume a little bit more, namely the second moment with an extra log actually converges. So this should remind you of the Keston-Stigum result. So this should be thought of as the d log d moment for the size-biased distribution, and that was indeed the offspring distribution in my branching process approximation. So this is very closely related to Keston-Stigum's theorem. So we'll take the weights to be IID with a general continuous distribution. No assumption whatsoever needed on mean or on sort of support, or just continuous.
Not negative?
Continuous and positive. Yeah, precisely, yeah. Because we're really thinking about it as modeling a time delay, or traversal time. Then it turns out that there's two universality results, so that this weight between two uniform vertices grows basically like log n times some multiplicative constant that depends on n, but converges to some limiting value. And in some cases you can actually interchange this gamma n by the limiting gamma, but in some cases you can't if the convergence is too slow. And if I look at this difference, then this converges in distribution to some limiting random variable. So the time delay it will take you to spread your rumor from you to an arbitrary individual in the network will basically be logarithmic, and the difference between this time delay and the right multiple of log will actually be a tight random variable. That's what this says. Okay? And then the number of people involved in spreading the rumor, which in fact for a rumor may not be such a bad thing to look at, because we all know that when a rumor is said many times, actually the rumor changes. So you could think of this HN also as being a measure for the quality of the information that reaches the destination. And it turns out that this satisfies a central limit theorem with the leading order coefficient log n, and also with a standard deviation that is of the order log n. And it's always Gaussian. So there's a high amount of universality in these results. It's always the same type of behavior here, the same type of behavior here, and then even the same behavior here. It's always Gaussian. And it turns out that also this limiting random variable has a high amount of universality in it. It's always of a similar structure. It's the log of a martingale limit plus the log of another martingale limit, IID from it, minus a Gumbel. It's always of that shape. Okay? So there's a high amount of universality here.
There's one question.
Yeah.
It's natural that suppose I want to control this network.
Yep.
So I'll just go to the big guys,
Yep.
tell them you can't spread rumor.
Yes.
And then what happens? Are there not, I mean, this is a general problem that you manage the...
I think the results will not change. Of course, the constants are going to change.
But they're not going to the...
No, not here, because here we're in the finite second moment regime. So that is relevant for the next theorem, indeed, because if we're assuming that we're in the infinite variance setting, then it turns out that the amount of time it takes to spread the rumor from source to destination is going to be a tight random variable itself. And there indeed you see this phenomenon that the rumor is spread through higher and higher degree vertices. So if you would chop it off, it could be that this is still true, but then the distribution of this will change and it will grow as you chop more vertices off. Very good question. But I think you would have to chop off basically all the vertices of degree n to the power epsilon, for any epsilon, for this result no longer to be true. But I mean, that has certainly not been proved. So what happens if tau is in between 2 and 3? Well, in this case, let's just stick to the setting where the weight distribution is exponential. That's actually very nice, because by the memoryless property, this actually means that the growth process locally is a Markovian process. That's actually pretty nice. And in that case, it turns out that again, the hop count satisfies a central limit theorem, even with the same mean and variance, asymptotically. And now the amount of time it takes you to spread the rumor between source and destination will converge. So this is super efficient routing, so to speak. The rumor will actually spread very quickly through the network. Now, it doesn't always have to be that this is true and this is true simultaneously in general settings. So here I'm looking at the exponential distribution. So you could also think about what happens for more general distributions. And then it's not always the case that this occurs. But this is what is generally true if your weight distribution has sufficient mass close to 0. So any distribution that you can come up with, a gamma distribution, whatever, will always have a situation like that. You really need extremely thin tails close to 0. For example, a tail that is completely 0 in a finite neighborhood of the origin, for this no longer to be true. So for example, if you were to take weights to be 1 plus an exponential, so there clearly there's no mass on 0 to 1, and the mass only comes after 1, then this result can no longer be true. Because then actually the time it will take you will be at least as large as the graph distance. And we know that the graph distance is log. But in fact, in this case, it turns out that the amount of time it will take you to spread the rumor between source and destination is very close to the graph distance. Because it's exactly 2 times log n over log tau minus 2, just like where the graph distance is. So this says something about the topology of the graph, because it says that not only is there a shortest path of this type, even if you were to put independent edge weights on them, you can even find a path that is short in total number of edges and short in the total number of additional weight on them. So there have to be many really short paths in order for this to be true. Because an average path is actually, an average shortest path is actually going to have a constant 4 here. right? Because you multiply with the expectation of this, which is 2. So apparently along one of these paths, you can achieve that path with very small additional weight. And that's somewhat surprising. All right. Discussion. Random weights have a marked effect on the optimal flow problem. Surprisingly universal behavior for passage percolation on the configuration model. And even the limiting random graphs, the limiting random variables display a large amount of universality. Proofs, again, of course, branching processes, because we know that the local neighborhoods look like branching processes. You can just put the edge weights on them, and then this is again a branching process, a continuous time branching process, and it's called an H-dependent process. Continuous time branching processes have attracted a lot of attention as well, so we can actually use that methodology also to study these kind of problems. Okay, I'm not going to say much about this. Let's not say anything about this as well. There's a lot of literature. I will send the slides to the organizers so you can have a look at that as well. And this concludes my course. Thank you very much for your attention.